All right, our next example for substitution into trigonometry is going to follow this pattern that I try to go back to time and again throughout these videos, which is let's take something really, really easy and do it in the toughest way we can think of. So let's take the integral of 9x minus x cubed dx. All right, now, indefinite integral rather than definite, we're going to find out that there are certain issues with that. And there's an obvious answer, right? We can figure it out pretty quickly. We better end up with, at the end, 9 over 2x squared minus x to the 4th over 4 plus some constant. Anything else, and there's an issue. There's some sort of a mistake. So over here, if we wanted to integrate it, something that we can do is we can take out a factor of x. Now, obviously, we cannot take that x out of the integral. We certainly can't write the integral of this times the integral of that. Those things would be completely incorrect. But within the integral, we can write this. This is completely correct. And most instructors would look at this and wonder what it is that you're trying to do. And I'm going to take this bit over here, and I'm going to use that to indicate that I'm going to go with a substitution into trigonometry. I'm going to want x squared to be equal to 9 sine squared theta, and therefore I'll take x is equal to 3 sine theta, which means that dx is equal to 3 cos theta d theta. Some of you might be thinking, why are we taking 3 sine theta rather than 3 cos theta? That'll work just as well, right? If you had 9 minus 9 cos squared theta, you still are able to turn it into a single term, into a monomial. The advantage of sine over cosine is that when I take the differential of sine is cosine, the differential of cosine is negative sine. So this allows me to avoid introducing a minus sign that will just create a place where I can make mistakes. So if I take this over here, then my substitution becomes the integral of x, okay, I know what that is equal to, times 9 minus x squared. I'm going to save a bit of time. I'm just going to write this right away as 9 cos squared theta d theta. Okay, make sure that you can justify this line, right? In a solution, in a test, in an exam, you want to have the line that's in the middle, but on these videos, we do like every now and then to skip a line. Make sure that you can fill in the missing details, because it's important to be able to do that. This over here, we can integrate it pretty easily. We can take simply u is equal to 3 cos theta and just hop at it from there. That seems a little bit easier than we want it to be, especially because what it's doing is almost reversing what we have over here. Almost, but not quite. So let's do it. Let's have fun with this. Let's take u is equal to, let's go with just cosine of theta. And so we're going to have du is equal to negative sine theta d theta. And obviously these substitutions are undoing each other in some way. That's fine. This is just because we are going through it in very much the longest way possible. So when we take this over here, 3 times 9 is going to give us 27, which we can take out of the integral sign. Sine theta d theta becomes du, give or take a minus sign. So let's put that over here, and we'll have du. And then cos squared is just going to be u squared. So this is negative 27 u cubed over 3 plus a constant, which, if we were dealing with definite integrals, then we would have taken the bounds over here, substituted to figure out what they are over here, substituted again to figure them out over here, and we'd be able to just plug them in. Because this is indefinite, we have no choice. We've got to bring this back to our original variable, which can take time. It certainly can take an awful lot of effort. I generally recommend, and I have in other videos, that if you have a definite integral, that you do change the bounds of integration throughout. And then the next bit becomes really easy. When you have an indefinite integral, you have no choice. So we want to take this thing over here, work our way back to the variable x. So u is equal to cosine of theta, right? Just as a reminder over here. So that means that in order to isolate for theta, we're going to have to take, well, I guess in this case we don't need to just yet. We're going to have to afterwards figure out how to write down x in terms of theta, but this will do for the first step. This is going to be negative 27 over 3. I can probably simplify that, times cosine cubed theta plus c. All right, let's simplify that right over there. And then cosine theta. Okay, cosine theta, I need to substitute for it, but what I have is x is equal to 3 sine theta. Okay, so x is equal to 3 sine theta. I could, if I wanted to, write this down as divide both sides by 3. You get sine is equal to x over 3. And so theta is equal to arcsine of x over 3. Okay, and then I'm going to need to worry about cosine of arcsine. Right? We can write it that way. That's perfectly fine. There are other ways of playing around with it. They lead us to the same spot. So cosine of arcsine of x over 3, the whole thing cubed, plus a constant. All right, this doesn't look like that. Not even close. So what's going wrong? What is it that is off about it? Well, the problem is when you have a trig function of an inverse trig function, then that's something that you can and should simplify. You have to find some way of writing out what that's equal to. Right? You don't have to do it in most other occasions, but because these do interact in a very positive way, in a way that gives us a lot of information, we should do it. So let's try to figure it out. There are a couple of approaches. Most engineers play around with famous triangles or just right-angled triangles in general. I prefer using the unit circle for this, but let's look at both. So method 1. Okay, so method 1. We're going to look at right-angled triangles. You pretend that x is positive and that it is of a reasonable value. We're going to write down over here, this is going to be theta. That's a theta as in this one over here. And you use SOHCAHTOA. So if theta is the angle that has sine equal to x over 3, then sine is opposite over hypotenuse. This is x, this is 3. And so we can use Pythagoras. This is root 9 minus x squared. And that allows us to figure out what cosine is equal to. Pretty straightforward. On the other hand, if I wanted to use the unit circle, what I would do is I would draw this over here. And if I have theta is equal to arcsine of x over 3, so theta is the angle, wherever it might be, which has a value of sine equal to x over 3. I can just put it right over here. This is going to be cosine, comma, sine. One way or another, I'm going to get cosine of theta, cosine of arcsine, is equal to the square root of 9 minus x squared all over 3. And so I can substitute this into these brackets over here. And I can see what happens. I can figure out what it is that I'm going to get. And so when I do this, I'm going to have negative 9 times cosine of arcsine, so root 9 minus x squared over 3, quantity cubed, plus a constant. Well, something is still a little bit off. Right? If I take this and I cube it, what I'm going to get is negative 1/3 times 9 minus x squared times the square root of 9 minus x squared plus c. So where did we go wrong? So we had to take a break. I had no idea what it was that went wrong. This over here is certainly not equal to that over there. So we went back and we looked. And by we, I mean me. And I looked at this over here. We've got x squared is equal to 9 sine squared theta. No problem. When I plug this in, I'm going to have x is 3 sine theta. Okay, that's fine. I have my dx, no problem. That shows up over here. But 9 minus x squared, that's going to be 9 cos squared theta. And because I've done this so many times, with this having a square root on top of it, I just immediately turned it into 3 cos theta, which when I multiplied with the dx, gave me the right answer. But that's incorrect. This should have been 27 times cosine cubed of theta. And so the difference is that we multiply this guy by 3. This will be negative 81, and this will be u cubed. And so what we get is a very similar idea, but we're going to have negative 81 times u to the 4th over 4 plus a constant. All right, the reason we decided to go back and correct it over here, rather than just to reshoot the entire video and then you won't know that we've made a mistake, is that in mathematics you make a lot of mistakes. And this is chapter 7. This is one of the most difficult chapters in terms of the fact that you're learning in a slightly different way. At the video we talked about at the beginning of this chapter, there is a different method of thought within this chapter than in the other ones. So it makes sense to have errors. It makes sense to make mistakes. You've seen them in other videos. We try not to hide them. We try to demonstrate that mathematics is dirty, it's messy. The things you see in a textbook are not the first draft. They're always at least the second, the third, sometimes significantly beyond that. Some of the proofs that you see took 100 years, 200 years to refine to the point where they're as nice as what you see in the textbook. So we make mistakes. This will be negative 81 over 4 u to the 4th. We plug in this value over here. That's still correct. All of this arithmetic over here is correct. This is the really important part. And so we end up with negative 81 over 4 times the square root of 9 minus x squared over 3 all to the 4th plus c, which is going to be negative 81 times 9 minus x squared squared all over 81 times 4 plus a constant. These guys disappear. And when we do this arithmetic, what we're going to get is this up here, give or take a different constant. So we're going to end up with x to the 4th with a minus sign, negative x to the 4th over 4. We're going to have negative 9 times 2x squared. An extra minus sign over here makes it positive. Divided by 4, we have 9 over 2x squared. And then plus some constant minus 81 over 4. This constant is different than that one. Let's put a little prime over here. Right, they're slightly different, but we have the same integral showing up at the end. So we can do these much longer ways, and you can see what happens. This we were able to do immediately. One line, and we're done. This method over here, mistakes are easy. The amount of time that we took on it is far greater. The room for more mistakes is pretty massive. We're able to get to the correct answer at the end, but it is much more difficult. The reason why we want you to do a lot of homework when it comes to this chapter is because of something like this. If you choose the wrong method, it won't necessarily lead you to a dead end, although it might. But very often it will lead you to a position where you spend far too much time and have too much room for error than you would otherwise.